everyone, this is Sanjeev Venkatram and welcome back to Business Insights. I'd like to spend the next 10 minutes talking about part 2 of applying the full complement of Microsoft BI and AI assets to the discrete manufacturing space. Note that this is also applicable to the higher education vertical. For those of whom who missed part 1, I've attached a link in the post. In part 2 now and in this video, I'd like to highlight 3 key points. 1. The ease of design and simulation of machine elements using Power BI, SQL Azure, and Microsoft Teams. 2. The ease of creating and deploying a live and interactive design handbook using Power BI and Microsoft Teams. And 3. And completing the design cycle, the ease of analyzing testing data and predicting performance in the field using Azure Machine Learning. With this, let's get right into the demo and onto Power BI Online. The dashboard here has 2 parts. The one on the left is the design guide that walks us through requirements and formulae for designing machine elements. I've used a compression spring here as a simple example. The one on the right is the actual designer. Now, looking at the design guide, an engineer sees general considerations for designing compression springs, which are 1. Space in which the part is to fit, namely the outer diameter and the length of the spring. 2. The availability of existing part numbers, which is a very important criteria. And then 3. The critical criteria for performance that stress induced in the spring due to applied force should be within permissible limits. Now below are the relevant formulae for calculating stress induced and force applied as the spring is compressed on or deflected by a certain amount. So let's move to the designer on the right and see how easily one can design this component. There again are 2 sections here, inputs and outputs. For inputs, I know the space in which the spring is to fit, so I select the relevant outer diameter and length. I then select the material of the spring, chrome vanadium in this case, and select other parameters I can play with, namely the diameter of the spring wire and by how much I can compress the spring, also called deflection. On the output side, we have the force acting on the spring and therefore the stress induced and a few other parameters. As design criteria, we want to make sure that the stress induced in the spring does not exceed the permissible limit as indicated by the red zone. We can then run a simulation by increasing deflection, and as you can see, both force and stress induced increases, and we make sure we select the appropriate wire diameter of the spring. This is to achieve the right level of compression while being in the permissible limit of stress. Now, one data point here to note is the spring rate, which indicates the relationship between deflection and force. Note that the value of 36 does not change as I compress the spring, which means the relationship between deflection and force is linear, a key point to note. One can play around with these inputs and different types of materials till we arrive at a reasonable design. As you can see, this is very straightforward. Another element I would like to focus on is the materials table here. Now this table is pulled directly from a database, which is SQL Azure. This is very straightforward to do. I open Power BI Desktop and click on Get Data and look for Azure as the data source. I then select Azure SQL Database, select the right table, and load this into the data model. As simple as that. Additionally, we have integrated a design manual, which conventionally is paper-based, and a designer, typically in Excel, into one single source, Power BI. Extending this concept, the full design manual can be contained in one Power BI instance with a tab or 2 for each element or component. So, we have a digital design manual and a designer in one self-contained source. Also, while we're here, let's look at how this information can be shared across team members. For this, I open the Microsoft Teams app. What I've done here is set up a team called Microsoft BI Experiences and added team members. Now for this team, I've included Power BI as a tab, among other tabs like File Share. Now what I'm going to do is to chat with a colleague of mine about the design we've been working on. Note that he's using Teams Online and I the desktop version. So I click the chat button and have a conversation with Alex, asking his opinion on the design and specifically the wire diameter. So Alex plays with this parameter, checks for stress values, and confirms the 12 mm as a suitable number. Do note that I could have done a phone call or a video call with Alex as well. Now to complete the design cycle, we must verify performance by testing the prototype of the spring. What you see here is an image of the testing machine with the spring under test. We compress the spring in increments and note down the force required to do so. With this, we have a data set that gives us force at each increment of deflection. We can then use this data to verify performance of our spring design and predict its performance in the field. For this, we'll turn to Azure Machine Learning. So we go to the Azure Machine Learning Studio and start a new experiment. We then add the data set as a .csv file and highlight the right columns, deflection and force. We then split the data as shown here into two sets. One set, or 70% of the data, is used to verify the relationship in the test data between deflection and force. Once we have the relationship determined and verified, we run this model on the remaining 30% of the data, meaning for each value of deflection in the remaining 30% of the data, we can predict the value of force. We then pick the right machine learning model, linear regression in this case. This is a key step, and the choice of algorithm is based on our design knowledge that the relationship between deflection and force is linear. We then add a step to train the model, meaning running the regression on 70% of the data. Now we move to scoring the model, meaning applying the equation we got through training the model to the remaining 30% of the data to predict outcomes for force. Finally, we evaluate the model that gives us an idea of how good the prediction is. With this, let's run the model. And in this case, it takes a few seconds. So let's look at the results. I'll visualize results of regression under the train model step. And as we can see, the coefficient we get is 36, much aligned with the spring rate we designed earlier. We then look at how good our prediction has been by visualizing the R-squared value under Evaluate Model. As can be seen here, this value is 99%, so a very strong correlation. With these results, we can be confident of the performance of the design component in the field. I trust this gives you an end-to-end view of how one can design, simulate, test, and predict performance of machine elements while collaborating with colleagues with ease. Further, as to how Microsoft BI assets can be used to design live design manuals, replacing static handbooks. Thank you very much. Please note that the views and opinions expressed in this video are mine and do not state or reflect those of Microsoft.